But anyway, we're going to turn to Module 17 in your book. And for y'all that are new in the class, you'll notice there's a lot of different modules in the book. And each one of them is specific to a specific subject. And whenever we were asked to come down and give these courses, they actually picked the courses that they would like to have presented to y'all here. And so this is one of the classes that was suggested, and so hopefully it's beneficial. A lot of it, you know, you really, when you put a book together, it's really only the basics. It really doesn't get into all of the principles and technologies that, like Bessie and I or any of y'all would like to present, but it does help with the basics. And for y'all that do not work in the distribution system, this might be something very interesting to you. For y'all that do work in the distribution, this is something you're probably used to doing every day. So hopefully the information is valuable and it awakens some of us, but you never know. So that's the most interesting thing. But let's look at the terminal objective, okay? Let me get my old thing up here. Terminal objective. Upon successful completion of this module, again, you and I as an operator, and Bessie and I are operators too. For y'all that are new, we're no different than y'all are. It's just that we've had a lot of good mentors through our career. And so we're sharing with you what we have learned from our operators that actually taught us throughout our career. So we as operators will be able to describe the common methods of water delivery to the public following treatment, water treatment. And that's the key. Water treatment personnel or operators, they treat the water to a quality and a standard that's safe to deliver to the public. But for y'all that work in the distribution, then it becomes our responsibility to make sure that it maintains that quality and it's still safe to use. And sometimes that's very difficult. So we'll talk about that. Now, the enabling objectives. Those things are to help support, or how do you say, in combat you have your terminal objective. You're going to take out an adversary. But you need certain things to be able to do that. And that's exactly what enabling objectives do. They're going to help us achieve our primary terminal objective. So first of all, we're going to discuss the different types of storage. And you know, we have ground storage, clear well, standpipes, and elevated storage. List the major components of the distribution system. You know, we have, some people have transmission lines, outfalls, we have mains, sub-mains, and then we have, sometimes we have laterals, and then we have our service lines going to our customers. And then we're going to explain the different aspects of pump usage for the distribution system. Why do we use centrifugal pumps rather than positive displacement? There is a reason. And so we'll talk about some of those. And then we're going to discuss the use of motor and motor installation and how it is important for the distribution system. And so those are the four things that we're going to focus in on, okay? And for y'all that are not in this area, this might be something that helps you understand their part of the system too. So storage reservoirs, what do they do? Facilities equalize demand on the water supply. Now what they mean there is normally if we are a surface water plant or a groundwater system, our systems might not be able to provide all the water necessary to our customers, okay? So what we do is during low demand, we're filling our storage facilities. That way when we have high demand, let's just say that I have a groundwater well and it puts out 1,000 gallons per minute. But my demand on that system is 2,000 gallons per minute. So we want a certain amount of storage so that during that high demand we can still supply and equalize the flow to the customer without jeopardizing both pressure and also quantity of water. And so they want a certain amount of hours of storage during those high demand times. Most of the time people do not use as much water at night, so we're filling at night and using more water during the daytime. And also for emergency use. Ask you a question. Is y'all's distribution system also used for firefighting? Yes, okay. Some systems are and some systems don't, okay? So we'll talk a little bit about that too. Low demand, storage filling. High demand, storage depletion, all right? Allows uniform pumping rates. And this is why the centrifugal pump is so important. Believe it or not, a centrifugal pump can pump against negative head. So what happens, we're filling the elevated storage tanks, let's say. And when it gets near to the top, it hits negative head. That means it cannot raise that water any higher in the elevated storage, okay? So that pump has to be large enough that it can fill that tower, okay? And so those are the things that we have to be aware of and to make sure that our pumps are large enough to fill. But as the tower empties, the amount of water the pump puts out increases. So as head increases, volume decreases. As head decreases, volume increases, okay? If I've got a 1,000 gallon per minute pump and the tower is completely full, it's putting out 0 water. All it's doing is maintaining that volume. Does that make sense? But as the tower drops, the pump is able to pump water into that tank to help keep it full, okay? So we have to look at that. Supplies water for firefighting. Now the EPA really doesn't have a standard, but AWWA has a standard that most states follow. Texas follows the AWWA standard. Here in Rhode Island, which standard do they follow? Do they have their own personal standards or do they use the AWWA? Do y'all know? You never know. And, but that's something you might want to be aware of and might even check on to find out what your state requirements are for firefighting. The only thing in Texas, we have one town which is required to have a minimum of 250 gallons per minute, and that's the city of Houston, our largest city in Texas. All the other cities are not required to do that due to the fact that they have a lot of folks living down there, just like I think it's the 4th largest city now. So that's one of the few, okay? Provides time for disinfection. And as y'all know, CT, Bessie's going to talk about that this afternoon. And due to storage, that provides the necessary time for the chlorine to react with all the critters in there and thusly lowering the numbers so low that they don't have an effect on the population, okay? So we're going to get in there. The basic thing, can you change the capacity of the storage facility? No. So the only thing that we can do to adjust for CT is what? Increase the dosage and raise the residual enough to where we can be assured that we meet the CT values for that particular system, okay? And then types of ground storage. Clear well is normally associated with surface water. Once the water, it's got a lot of turbidity in it, colloidal particles of organic, inorganic materials. We remove those by filtering and using chemicals. And then it goes into the clear well, which is a storage tank or ground storage tank, similar. And the water's clear. It's supposed to be pristine and pretty and all that stuff. So they call it a clear well. And in groundwater systems, they call them groundwater tanks because primarily wells are pumping in there and the water should already be pretty much filtered. You know, it passes through the different stratas of the earth and the sands act as a filter, okay? And meeting the Texas requirements, the state of Texas requires that every facility in Texas have a minimum of 200 gallons per connection storage. Now, each state can be slightly different, okay? But the EPA mandates that each state determine the amount of water for storage, okay? Now, when it comes to firefighting though, this is only for water supply. But if you're using your system for firefighting to get the best insurance rates, that must be my phone. I usually turn it off. I never get phone calls. I've got 3 since I've been here, and all of them have been the wrong number. And, yeah, crazy. All right, I apologize for that. That's my phone, so I interrupted the class. But insurance boards require certain amounts per person. To give you an example, they require 130 gallons per person to get the highest key rate with just, let me kill that thing. Pull out my rifle and blow a hole in it. Did you kill it? Thank you. Yeah. That's probably that same person called me yesterday.
You want me?
Yeah. No, a lady called yesterday, and I told her, I said she had the wrong number. You see what I'm talking about? And then you kill it. I don't even recognize the number. I think it's from China. But anyhow, they require 130 gallons per person. But they also require nearly 55 gallons of elevated storage. Okay? Now in Texas, the TCQ, our state agency, requires 200 gallons of ground storage, and 100 of that needs to be elevated. Okay? Up to a maximum of 5 million gallons of elevated storage. So each state is different. Do y'all know what y'all's capacities are here in Rhode Island? Any idea? Okay. Now, in Texas also, they allow you to use pressure tanks. Okay? The EPA allows you to use pressure tanks for small systems and even in large systems. In Texas, just as an example, and you can find out what your state requirements are, in Texas, if it's pressure tanks, the largest tank that we can use is a 30,000 gallons, and it's good for 2,500 connections, okay? But when it comes to, if you're only using ground storage, or if you're using ground storage and pressure tanks, then you have to have a minimum of the 200 gallons. Then you only have to have 20 gallons per connection for pressure. If you do not have ground storage, it's 50 gallons per connection pressure supply. Okay? So that's Texas. But Rhode Island, Massachusetts, all the states up here could have their own basic standard. Does that make sense? Okay, so that's something that you can look into, find out what your state requirements are. And that way you make sure you have the quantities needed for your system. Okay? Corrosion resistant screens. When you talk about designing a system, and I'll put this up on the board. I like to draw pictures and stuff like that. And some of the things that are required. Let's see, where's my pen over here? There it is. Okay. Oh, there's a black one. I like to use black. It shows up. Okay. Now, when you're designing a tank, let's say it's going to be a ground storage tank, and we're going to have our vent up here and our screen on here, and then might have a roof hatch and a lid, and then we're going to have a ladder over here, let's say, and then I'm going to have my overflow. Let's put the overflow over here too. Okay. And we're going to talk about the vent. First of all, the vent must be large enough to prevent both a vacuum when our boosters are running and also relieve pressure whenever it's being filled. If this is too small, there could be damage to the tank, okay? Now, the screen that's used to put around the vent must be 16 mesh made from either stainless steel or non-corrosive material. The thing that's required that anytime you rehab this tank, that screen must be replaced, because a lot of times people spray paint and the spray paint will fill in the screen, and you could create a vacuum or an pressurization because of the screen. Now, also the cover. The Safe Drinking Water Act now requires that that be tamper-proof. Most people are putting what they call the mushroom covers over the top so that people cannot reach up underneath and pour chemicals inside of your tank. Okay? Does it make sense? And that is a requirement. Okay? Now, on your entry, let's talk about the slope of the roof. The slope of the roof is 3/4 inch per foot of run, okay? So for every 3 foot, we must have a 3/4 inch rise. Does that make sense? And that's to allow the rainwater to run off of the top of the roof. Now, when it comes from the manway, when we're talking about extending it, it must extend at least 4 inches above the roof line, and the cover must be dust-proof cover that turns down at least 2 inches, and it must be locked at all times with a tamper-proof lock. It must be a shrouded lock or one of those covers where you have to stick your hand in there to unlock it, you know, one of those steel covers. And it must be locked at all times, even when you're there. If an investigator comes out and finds that thing unlocked, all hell breaks loose, okay? It must be locked at all times. The only time it's unlocked is when you're actually performing maintenance or something like this, okay? Now, when we talk about the overflow, the end of the overflow, remember, if this is the finished ground and I've got a 6-inch overflow, they recommend 2 times the diameter, inside diameter of the pipe. So if I've got a 6-inch, it would be a minimum of 12 inches above the ground, okay? And then we must have an apron to prevent soil erosion. If it should overflow, the water can flow out of the overflow, okay? The other thing, this cannot be tied into a storm drain or a sewer main either, okay? Now, it also must have a weighted cover. And a lot of companies use the baloney cut. You got your nice baloney cut and you got it hinged over here, and it's a weighted lid. Sometimes you'll see a weight weighted on here, and still the water can force it open. Can't be so heavy that it prevents it from opening, but it must be heavy enough to keep it closed. And the amount of gap between the end of the pipe and the cover is 1/16 of an inch. Okay, 1/16 of an inch. Make sense? Now, a lot of times overflows do not come all the way to the ground. If it should stop up in the air somewhere, then the ladder must be close to the overflow so that the investigator can go up there and check to make sure that the flap is properly installed. Does that make sense? Okay. Now, your ladder. It must be an anti-fall type ladder where you hook your safety harness to that thing. You climb up there, and that way you can get up on the tank if you need to. Okay? So the ladder needs to be next to the overflow in case the investigator wants to go up there and inspect it. Now, a lot of people use targets. Okay? How many of y'all use targets on your tanks? Anybody? A lot of times towns will use a target, and you'll have a thing with a target on it, and whenever the target is at the bottom, the tank is what? Full. When the target is up here, the tank is empty. So as the water fills, the float comes up and the target goes down. As the tank empties, the target comes down and it rises. This should be visible from the road, so that if you're driving down in your work truck, you can actually see the target. Now, on your tank, some facilities are required to have a gauge. The gauge is a head gauge. Believe it or not, they rather have it in head than in PSI. And there should be in 2-foot increments. and the minimum diameter is 3 inches. Okay? And the numbers should be visible as best possible again. So if I have a gauge over here, I can see it from the road again. Okay? If I have an access road driving up to the tank, I can look in there with maybe a pair of binoculars and see that gauge. Does that make sense? Now, the materials. Ground storage tanks can be constructed virtually of everything as long as it is pretty much lead free. Remember, no materials can have more than 8% lead, and your flux and solder cannot have more than 0.2% lead. Okay? Now, the paint that's used to paint the interior of the tanks must be lead free. And if you do use a metal paint, you can only use metal, aluminum hydroxide, or zinc oxide paints. Okay? Make sense? Okay, those are the only two approved by AWWA for painting those tanks. Now, those same requirements are for standpipes and everything else. Okay, for standpipes. The only thing, they do allow you to use galvanized steel. Galvanized steel is bolted, so you cannot weld it. But you cannot use galvanized steel for standpipes or for elevated storage, because being higher elevations, it's more difficult to maintain if they started to leak. And who wants to climb up there very high anyway, you know? So we go from there, okay? Corrosion resistant screens, 1/16 inch gap at overflow covers, entry ports, rims meets requirements. Capacity is 200 gallons per connection. This is only for what? Customer. If you're talking about fire, it's completely different, okay? Ground storage, and here's a few pictures of some ground storage tanks. I saw some out there on the wall out there, really some unique tanks. They're really nice. And primary roof access, not less than 30 inches in diameter, okay? Proper access provided when during maintenance. Painted, disinfected, and maintained to AWWA standards. There's 3 different ways of disinfecting. One is where you can actually spray down the walls. The other one is where you partially fill the tank 5%, you add your chlorine, then you fill it. And then the other one is where you add it as you're filling the tank, okay? And when it comes to disinfection, if you put it in by batch, then you have to wait a minimum of 24 hours before you collect your BAC-T samples. If you do it by injecting at the same time it's being filled, you have to wait a minimum of 6 hours for detention time before you can collect BAC-T. Now, if you fill your tank 5% and you go with the 50 milligram per liter dosage, then you fill it, then you know your chlorine concentration could be too high to run a BAC-T test. And so instead of draining the entire tank and filling it back up, you can fill and drain at the same time till your chlorine residuals get within a certain range so that you can take your BAC-T test, okay? Now, when you're taking BAC-T test, the main thing you want to remember is to do it right the first time, all right? If you do it right the first time, you take one BAC-T test. If it passes, then if it's negative, passes, you can put the tank into service. But if it fails, then you have to pass 2 BAC-T tests taken on 2 different days. So you take, say, one on Monday, one on Tuesday. Then it has to pass 2 exams. Does that make sense? Okay. No lead products allowed. Again, your materials cannot be more than 8% lead, flux and solder more than 0.2% lead, and no paints can have any lead in it at all. Coatings must be approved. Types of elevated storage. This is in Paris, Texas, right up on the Oklahoma-Texas border. And you can see that they used a concrete structure, and above the concrete structure is a steel tank. The requirements are the same. The only difference is when we talk about elevated storage. Draw a little picture over here again. I like pictures. What is elevated storage? if you live, say, in the mountainous area or the hill country, and you've got an elevated storage tank, and let's say this is my highest service connection, and I got people down in the valley. Okay, this is my highest service connection. Anything that is 80 feet above the highest service connection is considered elevated storage. So this amount of water in here would be considered elevated storage. So anything above 80 feet was what? Considered elevated storage above my highest service connection. Everybody on the same page? All right. So the people in the valley are going to have higher pressure than that of those people up on the slopes of the hills and stuff. All right. And pressure maintained by water column height. And I'll put this over here too. When we talk about the hydraulic gradient, let's just say this is the city, and over here I've got elevated storage tank. And over here I'm going to have a ground storage tank, and it's being filled by a well. Okay, now here's my town in between. Okay, and when the pumps are not running, I come into this pump, and it comes across town and up into this elevated storage tank. When this tank is full, and the pumps are not running, and nobody is using water, my hydraulic gradient is going to slope toward the outer extents of the town. Okay? Now, the reason is even though it might be, let's say it's 75 psi at the tank, but it might only be 70 psi way over here because of the friction in the line. The friction creates artificial head. So your hydraulic gradient is going to slope away. Now, let's say we get mad at somebody, we set his house on fire. Okay? Maybe it's the mayor. No. But anyhow, what happens, the fire department comes out here and they open up a fire hydrant, and the hydraulic gradient is going to drop off dramatically. They're opening up, fighting a big fire. But these folks on this side of town, their pressure could drop below that minimum of 20 psi. So what happens, the booster comes on, creating artificial head. The pumps are going to provide the necessary head, and so what happens, we end up with a hydraulic gradient shaped something like this. Okay? Makes sense? All right. And so you always want to have your supply side on the opposite side of town, and you're elevated on the opposite side so you get the benefits of the pumps. If you build the pumps next to the elevated storage, you're not going to get any benefit whatsoever. Does that make sense? All right. All right. And then, of course, yesterday we went over this. 1 foot of water column equals 0.433 psi. And, of course, if you want to know how many feet of water equals 1 psi, take 1 psi divided by 0.433 equals 2.31 feet. That's approximate number. So every 2.13 feet is equal to 1 psi. So if I have a tank that shows 60 psi, I can multiply 60 times 2.31, and that tells me how high the column of water is in that particular tank at that time. Okay? And vice versa. If I want to convert head into psi, I can divide by 2.31, or I can multiply by 0.433 and get the psi. Does that make sense? Remember that from yesterday? Okay. And then requirements for systems with 2,500 connections or more. Again, anytime you have large cities, they prefer that you have elevated storage rather than pressure systems. But in some states like Texas, we can have a single pressurized tank, 30,000 gallons is good for up to 2,500 connections. After that, they want you to have elevated storage. And I do not Do you know what it is? Did you look up and see what it is for Rhode Island, Miss Bessie?
I didn't.
Do y'all know what it is for Rhode Island, or the amount of the capacity of your pressure system if you don't have elevated? Yeah. And this is a large community anyway. You have several thousands of connections, so elevated is probably pretty much standard. Must meet ground storage criteria for your state. Okay. Maximum PSI. What they mean by 35 PSI is during normal operations, I must maintain a minimum of 30 PSI all the time. But during emergencies like firefighting, if I have a fire or something goes wrong, maybe I have a broken main or something and I have to isolate part of the town, I still can never drop below 20 PSI. The reason is, as pressure drops, velocity increases in the pipe, creating a vacuum. And if you have some deteriorating joints, then if your pipe is submerged, outside water can be siphoned in through the joints, and you could get contaminants into your system. They have said that it has occurred a lot of times. That's where a lot of problems have occurred, is through the vacuum effect through the joints. Okay? And of course, what is considered 35 PSI takes 80.85 feet to actually eat 35 PSI. But they consider anything above 80 feet above the highest service connection as being elevated storage. It's slightly lower than that. Okay? Close enough for government work, as they say. You know what they got. And then types of storage. Here's a good old standpipe. Again, you cannot use galvanized steel for standpipes. And the definition of a standpipe is the diameter is less than the height. Ground storage tanks or clear well, the diameter is greater than the height. Now, why do they use this? In a community where they have rolling hills or maybe even some mountainous area, they can put this on the high points of those areas and use it as both ground and elevated storage. And a lot of communities do that. Lots. I've seen them throughout the country as I travel. And so we go from there, okay? Resting on the ground. What they mean by that, we normally do not build tanks sitting directly on concrete or any other type of substance. The reason is we put a sand base under it. Because when water cools or gets hotter, it's going to do what to the metal? It's going to expand and shrink. And sand allows for that. But if it's sitting on concrete, it could cause what? Stress. And the stress could cause the tank to crack or start leaking. But also, it acts like a French drain, a weep. You want your soil sloped away from the tank. Like here, you want it sloped away. So if the bottom of that tank starts to leak, the water is going to seep out toward the edges of the tank. And if you start seeing soft spots around that tank, that is an indicator of problems with the floor, possibly. Okay? All right. Greater than the height of the diameter, greater than 80.85 feet tall is considered elevated storage, or 30. This is actually false nomenclature. It's 80.00, but anything above 80.85 will meet your 35 PSI. Okay? Usually built on elevated ground, which is true. Must meet elevated storage criteria, meaning like at this point, if this was the 80-foot mark, and this was our highest service connection, anything above that point would be considered elevated storage. Okay? Pressure tanks, if you notice, this is a pressure tank. This is up at Gainesville. And this right here, I think, is a 10,000 gallon pressure, or no, it's 5,000. 5,000 gallon storage tank. And you have to have an air compressor. We're located in this building is an air compressor. And the design criteria for a pressure tank is the top 40%, or excuse me, the top 20% is for compressed air. And then you can only draw a maximum of 40% capacity. Okay? That way you maintain some volume at the tank at all times. The reason is, If you draw the water down too low, you're going to create a vortex and you're going to draw air into your distribution system. So you have to maintain water in that system at all times. Otherwise, you could create problems. Does that make sense? Okay. And it's hydropneumatic, using compressed air against the surface of the water. Cylindrical in shape, horizontal to the ground most of the time. They don't have to be, but most of the time they're horizontal. Air mechanically compressed against the water surface, and storage maintenance, annual inspection. Ground storage tanks, elevated storage tanks, and standpipes must be inspected both on the inside and outside annually. Hydropneumatic tanks are inspected annually on the outside and every 5 years on the interior. Okay? They give you a little bit more time for the interior because they're sealed, you know, and so air, the only air in there is that from your compressor. And most air compressor air is very dry, so it doesn't add moisture to it too much, okay? Annual interior, exterior of tanks. They must meet 8 WWA standards, American Water Works Association, for y'all that might not be familiar. Corrosion protection. Corrosion protection can be paints, remember this. They must be NSF and meet the Food and Drug Administration standards. No paint can have lead or at all, and if you're using metal ion paint, you can only use aluminum hydroxide or aluminum oxide or zinc oxide paints with nothing in them, okay? Another way of corrosion protection is cathodic protection. It's where we use sacrificial anodes. We run an electrical current either through aluminum or zinc rods. The zinc rods have a greater ionization than the steel. Thusly, the ions are carried to the outer part of the tank that is submerged in the water. Anything above the water line is not protected, so you have to use other means to protect that tank. Make sense? Okay. And grounds kept, remember, most utilities are so understaffed that the first thing we neglect is the grounds around our own facilities. We have to take care of everything else. But remember this, the public has a perception of operators. They think that sometimes we're a little bit lazy. And I don't tell them they're probably right, but that's okay. Grounds must be kept though. If they see a well-maintained facility, grass trim, nothing growing up through the fences or the gates, and the grounds are well-maintained, tanks are painted, then normally the utility has a very positive image with the public. So just taking care of our own facilities is a very vital part of customer relationship. Yeah, it's easier to persuade them to give us a little extra bump every now and then to help keep the system going. And sanitary protection. Stored water must have disinfectant residual. Again, Miss Bessie's going to talk about that this afternoon when we get into the coliform rule. And just remember that we talk about CT, and we must, if in Texas we have to have a 0.2 free or a 0.5 total if we're using monochloramines. And at the furthest extent of your system in Texas, we have to have a 0.2 and a 0.5. A lot of towns might have different standards. A lot of states might have different standards, okay? So you need to know exactly what your state standards. I think a gentleman in here yesterday was saying they do not have to even chlorinate groundwater here, but they do it anyway. And so that's pretty good, okay? Yeah. And location of underground storage tanks. Remember this, anytime a tank is built below ground, you have to be concerned about seepage from groundwater into that tank. So the construction of that tank has to be what? You cannot use walls that are permeable, can you? You must use non-permeable materials. The other thing is, you want to build them in high areas, normally where groundwater does not accumulate. You reduce the risk by building it on areas where groundwater, or what we call table water, is not going to come in contact with that storage tank. Okay? Makes sense? Okay. Non-permeable walls and floor, and they still have the same requirements as if they were ground storage or elevated storage. All right? And so we look at those locations. Cracks, leaks must be repaired promptly and immediately. Prevent other contaminants from entering into the system. You know, if you have outside groundwater or table water and you're drawing water out of a tank or even a pipe or anything, you can get contaminants in through cracks and stuff like that in the concrete and through the joints. Must be disinfected after construction and after maintenance. Remember, there's 3 different standards that you can use. You can follow either one of those 3 methods. And distribution system, mains, service lines, and meters. Okay, when we start talking about mains and we start talking about a community, there's 2 things we have to consider, both industrial and population. Now, the EPA wants us to look in the future and at current historical information. Okay? You don't want to build a system that's too small that would hinder growth. But you also don't want to build a system so large that you have to flush the lines often and also possibly cause problems with quality. So you have to look at 2 aspects. Okay? 2 different things. But they normally would like you to look at industry and industrial growth 40 to 50 years into the future. Population, they want you to look 20 to 25 years into the future. Okay? Makes sense? So if I'm looking 50 years down the road, what kind of industry is going to be in Rhode Island? What kind of industry is going to be in Massachusetts? What kind of industry is going to be in anyone's community? Then you have to look at population growth. Are we going to stay a community type where we have individual homes? Are we going to have more growth with maybe apartment complexes? Are we going to have more growth with industry where they employ hundreds of people? So we have to look at all of those things into the near future. And so those are some of the things that we have to look at. When we look at service lines, this is the most difficult part. Normally in Texas, in other states, they use a 3/4 by 5/8 meter. That is considered the standard domestic meter. But some folks want larger meters. And it's due to maybe they're putting out a sprinkler system for their yards. Do y'all have sprinkler systems on your yards? And believe it or not, that is going to have a marked effect on the size of your main. Think of it like this. If somebody has a 3/4 by 5/8 meter and he's just using it to water his yard and take care of his own uses in the home, he's going to be limited to the amount of water that meter can put through it. But once you go to a larger meter, maybe you go to a full 3/4 by 3/4 meter, believe it or not, just that little bit additional water can affect the quantity of water delivered to a certain section of town. So you have to look at it from an aspect, how is that going to affect my overall system? Now when it comes to commercial and industrial, we have to look at a lot of things. Fire protection, does it meet the fire standards that our community has adopted? Remember, the insurance board requires certain amounts of quantities of water for them to get the best key rate on their insurance. So those are things we have to look at. And then the type of meter. Is it going to be positive displacement? Is it going to be a jet meter? What's the most common meters that we use here? Displacement? Yeah. A lot of people are going to jet meters due to high hardness in the water. You know, when you use PD, the hardness in the water is going to precipitate out on the inside of the meter. and it's magnetically driven. There's no connection between the meter and the register. It's turned by a magnetic field. You have a true magnet and a conductive material, a magnetic material, copper. And the magnet turns that copper, which turns the register. Well, as calcium builds up between the rotating assembly and the copper conductor, what happens, it slows down. It drags. It's like putting friction. So you're actually going to sell less water. Jet meters are the opposite. It measures velocity. So as it passes through the venturi or the throat, it puts a plate, it increases velocity. So you're going to, what? Sell less water for more money? Sounds good to me? No. Yeah, no. So you look at it from two different standpoints. Do I want to give them some free water? Or do I want to keep being able to fix my system? And it's a combination of the both, okay? And of course on meters, most states still use the PD as the most common, but jet meters are gaining popularity, okay? Valves, hydrants, pump stations. When we talk about valves, the most common valve that we use is a gate valve. And what's gaining popularity again is the resilient seat. You have a plug valve, it's coated with neoprene or rubber, and you have a smooth inside casing. The housing is smooth. There is no seat. And so what happens when you close it, the neoprene squashes down onto the interior of the casing and thusly gives you a complete seal. Double disc has a wedge in it, and as it hits the bottom of the valve, the wedge spreads the two discs out and it sets up against the seat. All right, now, if you're trying to throttle the water using a gate valve, double disc or single disc, what happens, the disc is going to chatter in there and you're going to wear away the surface of the seat, and the edge of the valve is going to be wore away. And if you barely have it open, the velocity is going to increase and it's going to wear away the seat and the surface of the valve. Thusly, you're going to have a leaking valve. All right? So I like the resilient seat personally. An old test question that used to be on there is, how do I know it's fully open or fully closed? And the old theory is it's 3 times the diameter plus 2 to 4. So if you have a 6-inch valve, 3 times 6 would 18 plus 2 would be 20. So anywhere from 20 to 22 turns, that valve would be completely open or completely closed. All right. Now, other types of valves we have in there is what we call isolation valves, and that is the gate valve. We use it out in the streets because we don't want to put everybody without water. If I have to go out there and make a repair, I want to isolate as small an area as I can. So by having gate valves strictly preventing me from having to put other people out of service, okay? But when it comes to flow control, there's many types of flow control valves. We have what we call special valves, like a check valve. A check valve only allows the water to flow up in one direction. Then we have like altitude valves. An altitude valve opens and closes based on head. Now, again, over here on this board, I'll show you. An altitude valve has a pilot valve that recognizes differential pressures, okay? And actually, it's a globe valve that has a pressure reducing valve built in and a differential pitot. So basically, here's my town, and I got an elevated storage tank and an elevated storage tank. Here is my ground storage tank, and I got a booster, and I'm coming to this side of town, and I'm going over here, okay? And my town is built in between. All right. Now, let's just say that both tanks are at the same elevation, okay? But let's say I get a fire here, and I have to open this valve up to fight fires. Well, this tank is going to be dropping, okay? The boosters are going to come on to give me artificial head so that I can fight that fire. But believe it or not, if there's low demand on this part of town, this tower is going to continue to fill. Okay? So what happens, I'm going to have an altitude valve built in here, and when it gets to a certain point, it's going to actually begin to close, to slow down the flow to go to this tower. And once that tower gets to maximum capacity, it's going to close. And then all of my pressure on this side of the system is going to be provided by my booster. Okay? Now, vice versa. As the fire department finishes fighting the fire and they turn off the fire hydrant, this tank is going to start to fill. Okay? Now, there's going to be what? A gradual filling of this tank. Water's still going into this tank. But at a given point, they're going to equalize. And then all of a sudden, the pressure is going to start dropping. And when the pressure drops, this valve will recognize that pressure drop and start to open, allow more water to come in here to maintain the pressure on this side of town. Make sense? Okay, so that's an altitude valve. It's a special valve. And then we have like globe valves. Believe it or not, a globe valve is what you used to use in the sinks of your home. All it has is a seat and a valve that came down against that seat to open it. And you could barely open it, or you could close it, or you could open it wide open. It had no effect on the valve whatsoever. Now, on the bottom of your fire hydrants is a globe valve. And a lot of people think that you're not supposed to partially open a fire hydrant that has the weep hole on it. You know, dry barrel that they use in the cold parts of the country. We use them in Texas anyway. Even though it doesn't get that cold down there, we use them because of the fact that it drains that fire hydrant. The firefighters can come out there and hook onto it without having to worry about water oozing out around the fire hydrants and all that other good stuff. So we use them in Texas also, okay? When the valve is completely closed, the weep hole is open. But what happens when you begin to open up that valve, the weep hole has a spring attachment to it now. Used to, it didn't. And it has a piece of leather on a piece of brass, and it slides down, covering the weep hole to prevent the water from running out of the fire hydrant. And thusly, we can open it up any amount. Now, the amount that we open up that fire hydrant is dependent on the pressure throughout your entire distribution system. Remember, you might not be able to open up that fire hydrant all the way because you have to maintain what throughout the distribution system? What's the minimum PSI? 20. So even though that fire hydrant might be able to put out 2,000 gallons a minute, you might only be able to put out 500 gallons a minute because you cannot drop that pressure throughout your distribution system to less than 20. So you have to check and know your distribution system to maintain that pressure. Make sense? Okay. And then we talked about we'll talk a little bit, pump stations, as you know, booster stations, provide artificial head while the elevated storage tank is full. They start dropping and it fills that tank and maintains the head throughout the system, the hydraulic gradient throughout the system. And all of this must meet the minimum standards for that system. Critical safeguards. Again, it's different for each state, but sizing your mains, placing your isolation valves strategically throughout your system so that you do not have to isolate too many people. But the main thing is when you put that system back into service, it has to be properly disinfected, right? And so we don't want to have to disinfect a whole bunch of areas if not necessary. And so we look at it. And of course, the greater than 20 PSI at all times, 35 plus for normal distribution pressures and stuff like that. Components, pipe materials. The most common material today is PVC and throughout the United States, polyvinyl chloride. But recently, the EPA approved high-density polyethylene. Are y'all using any high-density? Anybody using high-density? Let me tell you, I really like high-density polyethylene. The reason is they're heat-welded joints, and I guarantee you, you cannot pull them apart. So you're eliminating joints, okay? Thusly, I can install an entire system without any joints whatsoever. Also, high-density polyethylene can come in various colors now. They used to only come in black. Now you can get it in blue, white, green, purple, just many, many different colors. So if you're using what? Wastewater effluent that has been treated to a higher degree, we can use the purpley pipe. If we're talking about water, we can use the blue. If we're talking about gas lines, we can use yellow. But when we talk about sewer, then we can use the green, okay? So I really fell in love with high-density polyethylene, okay? But PVC has come a long way. They have what they call ultralight now. Used to, the only thing we could use was the old C900. It was very thick-walled, and the pipe was extruded. And that meant all the molecules were in a straight line, so if you dropped something on it, it would crack. It had to be very carefully installed into the ground, you know, putting the sand around it and all that, or pea gravel, whatever you use. But then they started to blow the pipe. It's blown now. So all the molecules are scattered. They're no longer in a straight line, okay? And it's much thinner, much lighter, but it has the same standard dimension ratio and pressure rating as the old C900. Okay? So the molecules being scrambled, it's actually stronger and more durable than the old C900. Okay? Makes sense? Okay. Now other materials is the old cast iron. Do y'all still use any old cast iron? Cast iron, there's a piece back there and it's cement lined. It's a little piece over there, and if you look at it, you'll see it. It's got about 1/4 inch of cement in there. That helps to protect it from corrosion. But then you see in the other ductile and cast iron over there, you'll see the tuberculation where iron has precipitated out on the interiors of that pipe. That is going to affect velocity and the carrying capacity of that tank, of that pipe, excuse me. Ductile is a better pipe. What you're doing, you're mixing carbon with the iron, and it makes it more flexible, more durable, and more corrosion resistant. Carbon actually acts as a barrier, okay? But the best thing about it, it's lighter, more durable, easier to tap, and it's normally used on the suction side of pumps because we need a good seal, and it's used in the side of construction of water plants and groundwater systems due to the fact that we need more strength there. It is also used under major thoroughfares where there's extreme load, okay? If we're using flexible base materials such as asphalt, the weight of the truck pushing down on that pipe is going to have tremendous weight, okay? If we have concrete or cement streets, there's less stress on the pipe because the street is made out of what? Primarily steel and concrete. The steel is the strength, concrete keeps the steel together. That provides the strength of that street. So we have to look at that. So wherever we have extreme weight, we have to look at both external and internal pressures, depicts the type of pipe that we might choose to put in our streets or behind the curb of a house, you know, in a residential area. You don't need the same strength pipe, okay? Now, when it comes to, how do you say, ductile iron, cast iron, steel, concrete, plastic pipe is most common, PVC, and high-density polyethylene, HDPE, okay? Pipe joints, we have several reasons for selecting pipe joints. Number one, on the suction side of a pipe, of a pump, we do not want air getting into the eye of the impeller. So basically what we want to use is a flanged joint. It's where we actually have a gasket in between two smooth surfaces, perfectly machined to give a bubble-tight, airtight joint, because we do not want air to get into the volute or the housing of that pump. All right? Now, out in the old days, a lot of people still have a lot of old cast iron where we use leaded joint paint, and it's called the what? The bell and spigot. And basically, all you had is the bell, and I'll draw that a little better. And anyway, we put some ram neck or hokum in here, and then we poured lead in here and we compact it. Remember the old days? How many of y'all remember doing that? Yes. I used to hate that. That was a mess. But then you would pack it. So there. Now what took the place? This is a test question on a lot of state exams. What took the place of bell and spigot is a mechanical joint. What they did, they welded a piece on here, and then they made a flange here like this, and then they put a retaining gland in here, and it went around the pipe. Then you put a bolt and nut on here, tornilla tuelca, and then you tighten it up, and it forced this gland in between the bell and the spigot. Mechanical joint, sometimes a test question. Then we have push on. Push on is real common, and a push on is where we have an O-ring, okay? And we have an O-ring in here. And the barrel comes in, seats, the O-ring seats. Now on the pipe, a lot of times you'll see a black ring. Have y'all ever seen that black ring on the end of plastic pipe or PVC? That is a warning device. When you push this in, they say that you should never be any closer than up to or 1 inch away. You never want to be past that. Okay, you want to maintain about 1 inch, because what happens, the end of the barrel will seat up against the back side of the PVC and possibly could crack it. Okay, make sense? All right, so that's the good old push on. And of course the flange, you just had the gasket in between, you had your pipes, and you put the gasket in and then bolt it. And this is an airtight joint. The other one is where we use threads. National Pipe Standard threads. And the only place we really use that is where on meters, water meters, we unhook the meter and we can lift it out of the yoke or the meter riser, and that way we can replace the meter and then put it back into service and all that good stuff. All right? All right. And maximum lead content, again, remember this. It's 8% lead in all materials and 0.2% lead in your flux or your solder. Okay? Cannot ever be any higher than that. And Bessie and I were talking about this morning. Right now, the MCL for lead and copper is a goal, and it's 0. I don't know if we'll ever be able to get to 0. MCL for lead is 0. But the EPA and them are trying to come up with a way to make us use different materials, I guess. And I was talking to a gentleman here yesterday that said that they're going to have to quit using brass or bronze because of the lead content. But I don't know if that's true or how true that's going to be. Lead-free joints. Tough.
In January 2014, the state of Rhode Island will not allow any service to go in, any brass to go in copper that has lead in it. All
Yeah.
non-lead.
Non-lead, huh?
January 2014.
Yeah. So they're going to have to go that engineering plastic. Engineering plastic's good, but it's very expensive. Very expensive.
No lead fittings are really expensive too.
Yes.
You can buy them, but
Yeah.
they're like 3 times the amount of them.
Oh yeah, that's what I said. It's all about money. Yeah. Yeah. Let me tell you something. I'm 64 years old and I chewed all the lead off the baby bed when I was born, and I'm still here. You know, you got to have a little lead to go. You know, lead gasoline made your car run better. Yeah. I'm from the old school, you know. Anyway, I'm sorry, but that's just the way I am. All right, distribute components. Again, this is the altitude valve. Here's the globe valve. This right here, if I can see it, there is your pressure regulating valve. And the most important thing is that little device right there. That is your pilot valve. That's what determines the differential pressure. Without that pilot valve in there, you could not open or close that valve very easily. Okay, that pilot valve is very important. Okay, and isolation valves cut off the system. Gate valves, most common. Control valves, such as this altitude, it's called a special control valve. And then we have globe, diaphragm, rotary. This is what we would almost call like a butterfly valve. And they really work good for low pressure but large pipes, because you can equalize the differential pressure on a butterfly valve. If you were looking at it, at the valve, you got a stem going down through the center, and we'll draw it this way, and you got your stem right here. So if you have, say, 100 pounds of pressure pushing up against this side of the valve, when you start to open it, it helps to open the valve, because it's going to swing back. And then the valve is going to sit like here. So the pressure is actually going to help to open that valve. If I had a gate valve, plug valve, and all this pressure is pushing up against it, then it's going to be more difficult. Sometimes we have to put a small bypass with another valve in here, because these are large valves. You know, 16, 18, 20, 24-inch valves are very difficult to open when you got 100 PSI pushing up against it. Just remember, Bessie talked about this yesterday, pi r squared times PSI, pounds per square inch, equals the pounds of force. And so if I had a 16-inch valve, you know, 3.14 times 8 times 8 times 100 PSI, that's going to give you the pounds of force on that valve. And it could be very difficult to open. So you might have to put a little bypass in there to assist you opening that there valve, okay? And one of the things we have is the fire hydrants. And this is a breakaway. We call it a traffic type fire hydrant. And the reason is that little piece right there has got a cut in it. So if a car hits it, it'll break off without opening up the valve. And this is a globe valve, just like you have in there. In Texas, the minimum opening right here through the valve is 5-inch. Each state has a different opening perspective. California is 6-inch, and Florida is 6.5-inch. The main valve assembly has to have a minimum. Do y'all know what it is here in Rhode Island for your main valve? 6-inch? Yes, sir. Texas doesn't care if your house burns down. It's just 5-inch, so we, go from there. But anyway, that's a globe valve, and here's that spring I was telling you about. The weep, you see that little piece right there? That is the weep hole cover. And so what happens when you start to open that valve, that little thing will slide down and seal off the weep hole to keep the water from running out. Right now, it's closed, and you can see it poking up a little bit back there. So it's actually sealing the weep hole below it is actually open, so it drains out on the system, okay? Now in Texas, our hose, what we call the hose nozzles, must be 2.5-inch, okay? This can be any size, and some states require a minimum of 8. In Texas, it's anything. You can go anywhere from 4 all the way up to 8, 10, whatever you wish. And do y'all have a booster pump requirement on y'all's fire hydrants? Anything? Don't. It's 4-inch, yeah. So it just depends, yes, sir. All right, and of course, this is the main opening device, and it's tied to the valve. And this is non-rising. So what happens, this goes down, this assembly goes down into the system. There's threads in here pushing this down, opening the valve against the flow. So if something goes wrong, the pressure will close that valve. How many of y'all have ever seen the Corey fire hydrants? The valve opens with the flow. So if you get a broken main or the fire hydrant breaks, it's going to stay open. And most people prefer that you put a valve on the system itself so that if you do have to work on the fire hydrant, you can isolate it. Now, the nut up on the top, the operating nut, you notice that there's brass on brass right here. When you close that valve, it is got a seat. You can see that brass seat right in here. And so what happens when you close the valve, you want to loosen that nut a little bit because brass on brass can tend to freeze up. So open it up where you can almost turn it just about a quarter turn. You can turn it with your hand almost. And that way the seat and the pressure hold the valve closed. Okay? Now, the minimum height between the ground and this operating nut is 16 inches. Okay? The reason is most fire hydrant wrenches will open at 360 degrees. All right? Very good. Now, this flange down here should never be any closer than 2 inches to the ground or more than 6. Because if it's improperly installed and if it's a breakaway or a traffic control type fire hydrant, then this will break off. If it's too low, they can't open it, plus they can damage it. If it's too high, the bumper hit right there, it's not going to do much good, is it? So we want it properly installed. But fire hydrants should be operated and maintained at least once a year. More often if they're in very high dollar industrial park areas where you got a lot of industry and stuff like that. Some towns operate them once a month or at least quarterly, because in those high dollar industry areas, you want to make sure that you can fight the fires, stuff like that. And color coding, if you're following AWWA, the bonnet is what must be color coded. And do y'all follow AWWA on your standards? Red is less than 500. Orange is greater than or equal to 500 but less than 1,000. Green is greater than or equal to 1,000 but less than 1,500. And anything greater than 1,500 or equal to 1,500 gallons per minute is color-coded blue. So that's the bonnet, must be color-coded. That's AWWA standards. That's not a state standard, that comes from the AWWA and the fire people. Okay. What can it be used for? Primarily firefighting. But how often do y'all have to flush dead ends here in Rhode Island? Monthly or?
Once a year.
Once a year, it's not put to the system.
On dead ends? In Texas, we have to flush dead ends once a month. More often if we cannot maintain chlorine residuals or if we have quality problems. Okay? But it's a good tool for flushing, and that's how we test our fire hydrants. During that time, we go out there and use them for flushing and test them to make sure they're working correctly. Assist in solving problems. If we're having trouble with maintaining pressure or quantities, sometimes they can show that there's a valve cut off someplace within the distribution system. They really help you know, if you have a fire hydrant here and a fire hydrant there and you have a line connected them and you put a pressure gauge over here and it reads 70 and over here it reads 30, there's something wrong in between there. There could be a valve off somewhere, you know, so you can use it for that. And bleed air from your mains after construction or after repairs and all that good stuff. And when we get into the meters, this is a nutating disc. It is a PD. This is Badger. And you can see there's the magnet and here's the conductive material. And as that thing spins, it turns the assembly to register the amount of water. It is PD, but the reason it doesn't surge is 2 reasons. Number one, it has multiple injection points. So as one of the sides empties, the next one is opening. Thusly, we don't get surge in our system. If we had a single valve opening at one time, there would be pulsation in your system, and the customer might not like you you know, and we also have nutating disc and oscillating disc, okay? And this is the oscillating disc right there. So, and the most common domestic is what? 3/4 by 5/8. And you can go larger, but how do you say, folks? Larger meters can cost you a lot of money because every time they flush the toilet, the commode, the bidet, depends on where you live, you know, you're only using a very small amount of water. And if it's not registering that water, you're losing income. And it can be substantial, and it depends on where you are. And so you want to use the proper meter. Propeller, compound, and magnetic meters. Propeller, turbine meters are primarily, they call them propeller. Actually, they're an impeller propeller. They're a propeller, they're just like the prop on a boat, but they're inside of a housing. They're inside of the pipe. The pipe acts as a housing. So the propeller has the similarities of an impeller. And so as the velocity increases, the revolutions or the RPMs of the propeller increases. So really it is a impeller propeller because it's inside of a housing. On a boat, it's out in a large lake or river, and thusly it's more like the propeller. Propels you forward by thrusting the water backwards, you know. Okay. Magnetic meters are primarily used in wastewater. They can be used in water because magnetic meters have to pick up something in the water, a magnetic field. It measures voltage. So as water passes through, voltage increases. And so as voltage increases, the volume is calculated using that rise in voltage. So it's a magnetic field that picks up those impurities in the water, primarily used in wastewater. And then compound meters, if I have a large business like a school, this used to be a school. Well, at times, you're only using very small quantities of water. And so the positive displacement meter is going to measure the volume of the low flow. But then you have gym or football or basketball or whatever it is, sports, and all the kids go in there to take a shower. Well, a small PD meter would not register that water very accurately. So we have a compound meter that has a propeller or a turbine meter built into it that measures the high volume. And once it meets a differential pressure, then that valve will open. But as differential pressure decreases, then all of a sudden that valve will open up. On each side of the valve, the pressure has to be equal. If it's not equal and the pressure on the distribution side or the customer side drops, it opens that valve. And thusly it'll read, okay? Makes sense, hopefully. Positive displacement meter for residentials can be jet meters. Utilities income is based on that meter. The AWWA recommends that you test meters every 10 years, residential meters every 10 years. Now, if you have a lot of hardness in your water or if you have a lot of corrosion in the water, you might want to check it more often, 5 years, okay? But all compound meters and all large meters must be tested annually, okay? Because they're using large volumes, and just a small change in accuracy can cost your city a lot of money, okay? Now, normally we use turbine meters on our water wells or on our surface water treatment facilities because we're pumping large volumes of water, and we want to be able to compare the raw water pumpage to what actually we provide to the customer. Normally, they say 10% loss. But if you think about it, 10% loss can be millions of dollars throughout a year. A lot of towns try to keep it less than 5%. That's considered acceptable. What is considered adequate is 10%, but what is considered the top of the line, or it optimized is less than 3%. Optimized is less than 3%. All right. And pipe installation, main installation, separation distances. Now, each town is different, but normally when we talk about separation between water and wastewater is a minimum of 9 feet. Okay? 9 feet. So if I have a water main and a wastewater or sewer, the minimum distance is normally 9 feet. Okay? Is that always possible? No. So if I have a water main and a sewer main running parallel, then one of the standards that's AWWA standard, but each state might have a different standard. Just to give you an option, there's many options, okay, is if this was my water and this was my sewer, then from this wall to this wall is 4 feet, and this way is a minimum of 2 feet. From inside wall to inside wall, from inside wall to inside wall. Okay? And then the sewer must be constructed of at least 150 PSI with watertight joints. Okay? There's different standards for different. If they're crossing, if I have a sewer passing underneath the water main, this would be my water. So here's my water, here's my sewer. Then the joints must be centered. Okay? Centered. If I was looking down this way and here's my water main, it must be centered under the joints. That way I have a separation between the ends of the pipes and the bells. All right? This sewer must be 150 PSI with watertight joints, pressurized joints. Okay? If it's in the distance between the water and the sewer is 2 feet. If it's any closer than that, then you're going to have to encase it and put it in cement stabilized sand to give you more protection. Okay? Things like that. And this is all found in your book, in your own requirements, state requirements. Okay, trenches. Bessie talked about this yesterday in safety. But anytime a trench is built, from the top of the ground to the top of the pipe is recommended how much cover? In Texas, it's 24 inch. AWWA recommends that the top of the pipe in areas where you have frost line be below that frost line. Okay? So how far does the soil freeze down here? Do y'all know how far down it can freeze during the winter? How about 4.5 feet? So AWWA recommends that the pipe be below that. Okay? Depends on what part of the country you live in. Texas, we don't have to worry about that. We don't have the permafrost like other towns do. So we have a minimum of 24 inches. And I don't know. I think they drink bottled water. I don't know. That'd be a big problem. Yeah. It's danged if you do, danged if you don't. I don't know. You know, Miss Bessie?
I don't, but I will be looking into it.
Yeah, I get all kind of ideas. You know.
You said you were up in Alaska yesterday. Was it hurt?
Oh, no. I said I wanted to go to Alaska.
Oh.
I want to go up there and get me how do you say, some of them big fish they got up there. Every time I see a show, they catch them big, what do you call them things? Walleye? Is that, yeah, okay. Trenching and proper trenching. And I'll just give you an example. Each AWWA and ANSI have some really good standards, but normally your trench, if I'm setting a pipe in here, the AWWA wants you to have 6 inches of select material. In Texas, we can go as little as 4. It can be 4 inches or 1/4 the diameter of the pipe, whichever is greater. Okay, but 6 inches. And then they want you to, what they call haunching of the pipe is where you take a shovel, and I mean shovel. They don't even want you to use a front end loader or a backhoe or anything. You pour the sand or the select material directly on it in an hourglass under here, and then you compact it up to the spring line. Okay? Y'all remember those? How many people do that? If they're here, they ain't in this room. It ain't my town, I guarantee you that. We just pour it in real slow. Okay? We compress it so that we get a good haunching of the pipe, and then we're going to put it in 9 to 12 inch layers, compact it until we have a minimum of 12 inches above the pipe. Okay? Now, what they say is that you need at least 6 inches on each side for a total of 12. Now, it doesn't have to be completely centered, but it should be as near center as possible in your trench. Okay? And remember, if you're using ductile iron, the flexibility is about 5% flexibility. That's a tremendous amount of flexibility. I would never do that amount because you're pushing that pipe to the greatest extents. But if you're going to have to flex that pipe, it's better to put flexible joints, you know, the bending joints, to take care of the deflection, because you don't want to have to come back and repair this pipe later. Now, there's 2 different types of corrosion with pipes. We have what we call galvanic, and then we have electrolysis. And electrolysis is where you have natural currents of electricity passing through the earth. Remember, the earth is a giant nuclear reactor, and it's got an iron core. And so there's magnetic waves passing. If you go up to Alaska, they call it the aurora, or the northern lights. If you come to Texas and you go to Marfa, they call it the Marfa lights. They call them big fireflies out there. And you ought to see the people go out there and watch that thing. But nobody tells them the truth that it's a magnetic field, and the way the sun hits it, look like 2 big giant fireflies out there. People do the weirdest things. But anywho, that is passing through there. So ion stabilization, it's like osmotic pressure. If you put salt water and fresh water side by side, and you put a membrane in between it, cellulose membrane, the ions from the salt water do not pass into the fresh water. The ions in the fresh water is a greater concentration than the ions in the salt water. Remember, hydrogen ions are going to equalize the hydrogen ions on both sides. So fresh water migrates through the membrane and into the salt water to equalize the hydrogen ionization. Okay? Same thing with pipe. It's looking for ion stabilization. So it's going to carry the ions away from the pipe and into the soil, and thusly you have what? Pipe failure. So a lot of times we're going to put sacrificial anodes on there to help protect that there pipe, or dielectric protectors on it. A lot of times when you're using ductile or cast iron or steel pipe, they'll put it inside of a visqueen sleeve, black plastic sleeve. Have y'all ever done that? Anybody ever done that? It's just like black plastic paper, you know, you just wrap it, but it's a tube, and you slide it over it while you're putting the pipe down. The other one is galvanic reaction, and that's where you actually tap like brass or bronze into, say, cast iron or ductile steel. Again, ionization. Remember, the hydrogen ions have to be in balance. So what happens, the ions from the steel are going to be carried over to the brass or the bronze. Thusly, we have what? Metal stress and fatigue, and eventually a leak. So they prefer that you use what? A tapping saddle that's been protected, You have a dielectric protector in between. You put the brass saddle into a brass valve. And then you are protecting the pipe from galvanic reaction. Does that make sense? Hopefully. Okay. And things like this. Texas, they recommend 30 to 60 minimum. Absolute minimum is 24. And then we talked about trench safety yesterday. Just remember, there's 3 classifications of soil, and then you have stable rock. Some people call it 4 classifications of soil. But you have stable rock, and remember the slope for stable rock is 0 to 0. You got to run to rise, and I'll put this up here again just for review. You have stable rock, which is run to rise is 0 to 0. Class A soil is 3/4 to 1. Class B soil is 1 to 1. And C is 1 1/2 to 1. Okay? So most soils are classified B. In Texas, most of them are B. So if I have a trench that is, say, 10 feet deep and 3 feet wide, then I'm going to slope back 10 feet, 1 to 1, 10 feet, and that is to help protect the person, okay? And you can use shoring, you can use benching, but this is known as the maximum allowable slope. We used to call it the angle of repose, yes. And but if you come in here and you use a trench box, then the trench box should extend at least 12 inches above the rim of the trench. And also you must have a ladder. Any trench that's 4 feet or deeper, you have to have a ladder. They must be within 25 feet of all personnel. And it must be tied off, it must be secured, and extend at least 3 feet above the rim. Okay? And this is for any trench that is 20 feet or less. Anything that's greater than 20 feet, then you have to have an engineer design the safety device. Okay? And now, in all previously excavated areas, I don't care if it was stable rock A or B, it will always be a C after that. Okay? So if you're excavating in any area that's been previously excavated, it'll always be a Class C after that. And the reason is the soil right next to it could be a trench and thing. You never lay water or wastewater lines in the same trench. All right? Any trench that's 5 feet or deeper, you must use shoring or some kind of safety device. The spoils must be 2 feet from the rim of the trench, never any closer. And that's in perfect condition. Remember, all standards are based on perfect conditions. How many of y'all ever worked in a trench? Anybody? Has your feet ever been stuck in the mud? That's a felony offense. You can go to jail and sit next to Big Bubba for a long time. You can never get in a trench that the floor is unstable or it's saturated. You have to use shoring. You have to put down flooring and everything else. Remember, all standards are based on perfect soil conditions. If not, you put in Conroe, Texas, Miss Bessie can tell you about this. We had 2 people drown. Their feet were stuck in the mud. The trench was 8 feet tall, filled up with water, and they couldn't get them out, and they drowned. Sanchos moved in. Somebody got to take care of Mama. So, you know, you don't put yourself in jeopardy ever. And I'm telling you the truth on that. Okay. So remember those things. And then talk about that. Minimum 4 inches or 1/4 diameter. AWWA, I did that a minute ago, is 6 inches. Or ANSI is 6 inches. Okay? Backfill trench after bedding. Remember, compaction is very important. You want to get it back to as near the density of the original soil. If you don't, it's going to settle. And then you're going to be coming back and refilling in that area, especially in streets, stuff like that. Bed with tamp, sand, or gravel. I love gravel. I love pea gravel. It acts like a French drain. It carries the water away from the pipe. If you use sand, if you go into a real dry year and you get cracks in the soil, the sand dissipates or moves and you lose your sand. Gravel, I like to use that 1/2 inch pea gravel. It works wonderful around pipe. It acts also like a French drain, and it's much easier to work with than sand in a lot of cases. You can notice right here, you got a good embedding. You notice that this is sitting directly on the bedrock. This is correct. They hollowed out for the bales. And here, this is wrong. They put the pipe in, they braced up under here, but they're gonna, if they don't properly haunch that pipe, it could get pressure pushing down. And here you got a mound of bedrock right there. It could cause a saddle type thing or a seesaw effect and crack that there pipe, and we'll be in bad trouble. Okay? Pipe bracing, again, is very important. It depends on the type of soil. Okay? That depends on the type of thrust blocking. Okay? Like on a fire hydrant, I'll show you, this is what the ANSI recommends for fire hydrants. So if you ever install a fire hydrant, here's your main over here, and here's our, we're going to come over here, we're going to have a tapping saddle. They recommend using flange because then the flange acts as a thrust block. Okay? You come off of here with the flange fitting, and then you're going to put a flange valve in here. Okay? A flange valve. This is so you can isolate the fire hydrant if you need be. Okay? And then you're going to come over here and you're going to have a flanged fire hydrant. Okay? And back here's the back. Now, underneath the tapping saddle, you're going to use a 2x2 foot block. Normally 3 inches to 4 inches in thickness because you want at least 4 inches of bedding. So we're going to set that on the thrust block. We're going to do the same thing underneath the valve. And then we're going to put a thrust block underneath the fire hydrant. 2 foot by 2 foot by 3 to 4 inches thick. We always went with 4 inch because of the fact that we wanted the 4 inches of bedding underneath the pipe. Okay? Now, after that, you take a steel plate and you place right behind the fire hydrant. And then you fill this in with concrete with an eye bolt. That way, if you ever need to remove it, you can lift it out with your backhoe. Okay? Then you're going to fill it up to the top, say here's the end, with pea gravel. It acts like a French drain, so your weep hole will drain into this French drain. You cover this with ground cloth or road cloth. It's permeable cloth that keeps the soil out of your pea gravel, and then you go ahead and backfill accordingly. Okay? Now, you'll notice that I have a block under the valve, under here, and you want to put a plate back here and also pour a thrust block. Because pressure is pressure. You remember a minute ago we talked about, let's just say that we have an 8-inch valve on the end of a line. So we have an 8-inch line, and let's say it's 75 psi. So if you take pi 3.14 times 4 times 75, took 75, let me erase this off there. Okay. Times 75 pounds or psi. And somebody got a calculator? Multiply that out real quick. Anybody got a calculator sitting around? Oh, he's got one.
The engineer has
10 4. 3,768. That's a lot of force. And can you imagine if that hits you in the kneecap? Yeah, that hurt. If that thing should blow off, you're going to have a ton and a half hitting you right in the nose. That would hurt. And that's a lot of force. So that's why how dangerous it is. Okay. And so proper thrust blocking is very, very important. Bracing placed at the bend or, however you want to design it. You're just trying, if you have water flowing in two directions, you're going to need a double thrust block. Because if I isolate it on this side, then I'm going to have pressure coming from this way. If I isolate it from this side, I'm going to have pressure coming from this way. So I might have to double thrust block. Just like I said on that one over there, you have to double thrust block a little bit, okay? It all depends. And then sanitation, all trenches should be clean and dry. Remember, all trenching is based on ideal conditions. If the ground is saturated with water, then I have to take additional precautions, always, okay? And ditch water should not enter the pipe. Most pipes are delivered with a plug on the end. Do y'all get y'all's pipes with plugs on the ends to prevent critters and stuff from getting in there? You don't? Well, before you put it in the ground, always check for critters. One time they installed a 40-foot piece of pipe, and there was a family of coons in there.
Oh, gee.
Yes, and there was 12 coons in there, and they never got that thing to pass a back T sample. They opened it up and flushed it out, and all these dead coons come rolling out of there. Yeah, 12 coons. Mama, daddy, and all the babies. Hee-hoes and hee-haws. So that was pretty good. All right, maintain sanitary controls and conditions at all times. You don't want to set your new pipe on the ground, especially if it's rainwater, could get on the inside, then it's just more additional work for you to clean. You can never use used pipe for new construction or even repair. Okay, remember that. It must always be new pipe. Okay, swab pipe with hypochlorite solution. What they're meaning there, most people, if you go down to your, like Walmart, and you buy NSF approved bleach, it must be NSF. You can call your local state agency and they can tell you if they're approved or not. Or you can get it off of the MSDS sheet. A lot of times they don't put it on the bottle anymore. So you can get the current MSDS sheet for that particular product. You can go on to Walmart webpage and you can download all of their MSDS sheets, their material safety data sheets, and get that information. Swab it out and make sure it's clean. A lot of people buy the tablets. They're stick-on tablets. They're 65% chlorine, HTH, and they stick to the top of the pipe. And they put them every joint. They'll put one tablet. That's 3/4 pounds of chlorine, and it works really well. Okay, have y'all ever used those? Yeah, they're real nice. Have you ever used them, Miss Bessie? Mm-hmm. Yeah, they're nice, aren't they? Yeah. And then never leave installed pipe with open ends. Remember at night, cover the ends. You never know what could crawl in there. One time this happened in Las Vegas. They were putting in a 24-inch pipe. Luckily it was storm. And some kids got in there and they started laying pipe. And they came in and locked it all in. And those kids were in there overnight. And if the pipe is just big enough for a little kid to get in there, they'll do it. You know, I was always in trouble when I was little. And if there was a pipe to crawl in, I would have been in it in a heartbeat. I was never claustrophobic. I should have been, but never. Okay, so go from there. 3 methods of chlorination for mains. Tablet, we just talked about. Continuous, that's very difficult to do, but it can be done if you have a portable injection system where you use a 150 cylinder or something like that. They do make them, but I don't like to work with gaseous material. I'd rather use bleach or HTH. And then a slug. And the way you do a slug, like we talked about, we have fire hydrants. So basically what you're going to do is you're going to have a valve, your main, you're going to have your fire hydrant. Let's say I'm going to be disinfecting. I got a fire hydrant here and a fire hydrant here, and I got a valve here and a valve down here. Okay, this valve is closed. So what I'm going to do, I have to disinfect according to AWWA standards. Your state might have additional requirements, so you have to follow your state's requirements. And what I do, this fire hydrant's open, this valve is closed, this valve is closed. The line is brand new or I've just repaired it. I've got both fire hydrants wide open, and I'm going to take a funnel and I'm going to mix up a barrel of HTH, and I'm going to figure out my dosage. And then I'm going to crack this valve, and I'm going to slowly pour the HTH mix into the fire hydrant and allow it to travel down until it's all the way to the end. Now, you don't want to pour it all in there at one time. You want to take your time and pour it in so you get disinfection throughout the entire distribution system. Okay? Now, after I've got the line filled with the HTH, I'm going to leave this valve cracked open until I bleed out all the air out of the system. And then I'm going to close that valve, and then I'm going to leave it closed for the proper amount of time. Now, I poured the bleach in this side, or the HTH. Now I'm going to keep this valve closed, and then I'm going to open this valve and close this fire hydrant, flush all the highly chlorinated water back in the opposite direction. Okay? Now, I'm going to dechlor this. You cannot put that super chlorinated water into the bar ditch. You can kill a human being, get a couple days in jail. You kill a fish, they're going to send you to Abu Ghraib and waterboard you. Yeah, you know what I mean? Fish have more value than people, okay? So make sure you dechlor. You can use sodium sulfide tablets. You can use sulfur dioxide, something like that. We always use the sodium sulfide tablets. We bought a basket. We hooked it onto the fire hydrant, and then we cracked it open, and it bled through there, and we checked the chlorine with our little tester and making sure the chlorine had been dechlorinated out reasonably. You're never going to get it to 0, but if you get it down to 1, 2, you're going to be okay. It's eaten up pretty quick by sunlight, especially. Okay. Table 7.1 provides detail. After disinfection, flush lines, we take back T samples. And back T samples, if you follow AWWA standard, it's different than state standards. Texas only requires us to do 1 sample per 1,000 feet. So if we repaired, say, 2,500 feet, we would take 3 samples to the nearest 1,000 feet. AWWA used to require 2 back T samples taken on 2 consecutive days. So you did 1, the next day you do another. I'm glad we never had to do that. Man, we'd be taking samples all the time, okay? So follow your recommendations on that, okay? Flushing, depending on your state, depicts on flushing. We have 2 types of flushing. We have what we call conventional, is when we might have low chlorine, we might have water complaints, or something like this. And so we're going to go out there and flush a general area. The second type is what we call unidirectional. Unidirectional is where we annually flush the system. Another type of flushing, if you're using monochloramines and you're getting this zooglial growth inside of your system, you're going to have an abundance of ammonia. And when you produce ammonia, it's going to convert the monochloramines to di and trichloramines. You're going to have taste and odor problems, and then you're going to have trouble with the customer, and they're going to come after you. And some of them people are pretty big, you got to be careful. So unidirectional is where we start off at the plant and we work our way out to the furthest extents of the system, bringing fresh water and cleaning the main. Now also, if you're using monochloramines, we need to get that zooglial growth out of there. Depending on your state agency, you can turn off the ammonia, and then you can use free chlorine, turn the concentration up, burn the zooglial mass out, flush it at a reasonable rate, normally around 4 to 5 feet per second, and then you can clean that line, and then after a couple days, turn your ammonia back on. All state agencies have recommendations for that, so you must follow your state's recommendations. You want to add anything to that, Miss Bessie?
No, that's good.
Okay, so we look at that flushing program. Flush dead ends at least once a month, but again, I don't know exactly what your state recommends, but in some states it's required if you have dead ends, you flush them monthly or more often if you have chlorine residual problems or if you have complaints, quality problems, okay? It helps to reduce slime, scale buildup, and red water. red water, there's two types really. There's actually where we have corrosion and we have iron in the water. It is suspended. And then we have what we call true color. It is dissolved in the water, and normally it comes from bacteria that eats on certain things, and it actually dissolves into the water. So we have true or permanent type color, and then we have temporary, which is in suspension. Most of it is just like that pipe over there in the window over there. It's tuberculation. It tuberculates out and forms nodules on the pipe, and then you have to go in there and clean it out or replace it every now and then. Okay? Brings fresh chlorinated water to contaminated areas, reduces chlorine demanding materials, and Miss Bessie's going to talk about that this afternoon. And flush carefully to prevent damage. Remember the recommendation, and let me show you how to do that real quick because I'm very interested in this. Let's just take, I'm going to be flushing 8-inch main. Okay, 8-inch main. Okay, and we know that every 100 feet of 8-inch mains holds 261 gallons of water. Okay, every 100 feet. You get that by pi r squared times the length times 7.48 equals gallons. Okay, so if you take 3.14 times 0.333 times 0.333 times 100 times 7.48 equals 261 gallons of water. So every 100 feet. So let's just say I had that fire hydrant here and a fire hydrant here, and I had a valve here and a valve here. And let's say it's 525 feet. Now we know, let's just say my dosage, we're going to use Texas standards, is 500 parts per million or milligrams per liter of chlorine. So all I do is take my million gallons times my 8.34 times my milligrams per liter equals pounds of HTH. I'm going to be using 65%. So I'm going to divide by percent active ingredient. So you take the 0.000261 times 8.34 times 500 equals, and if somebody multiply that out for me, and then divide by 0.65. Okay?
Syntax error.
Tic-tac-toe. Would you come up?
I got a syntax error.
I'm sorry.
Point 1, 2, 3.
Times 500 divided by 0.65 equals
There we go.
1.7. Okay, so it's 1.7 pounds. Okay, that's what we're looking at. So 1.7 pounds. All right, so what I'm going to do, that's per 100 feet now. This is per 100 feet. So now I'm going to take this and divide this by 100. That's 5.25 times 1.7. And so that'd be around what, 11 pounds? So I'm going to mix up 11 pounds of HGH into a drum. Mix it up, and then I'm going to crack this valve and slowly pour it in here, fill this up, allow it to sit for 30 minutes, and then I'm going to dechlor and flush it out. Now I have sanitized or disinfected that main. Now here's the thing, the AWWA recommends that you use 2 times the volume for flushing at a certain velocity of 3 or 4 feet per second. So let's do that. Okay. So now I've got to flush. Now we know that each 100 feet holds 261. Okay, each 100 feet holds 261 gallons. So I'm going to take 525, divide by 100, times 261 equals. So that'd be 5.25 times 261. What do you got, Miss Bessie?
What .25 times 261.
One
Hmm,
point three seven?
Hmm?
1.37?
One, well, it can't be that.
1,307.
1,370.
70.
Let's just put 70. Okay, now they recommend minimum of 2 times the volume, times 2. That's 2,740 gallons. Okay, now 3 feet per second is minimum. They recommend 4 feet per second. Okay, so now I need to figure out time. Okay, when you have a circular pipe, is GPM equals diameter squared times 2.448 times the feet per second. Okay, so we're going to solve for this. We have an 8-inch, so 8-inch squared times 2.448. We want to go 4 feet per second. So this would be 64 times 2.448 times 4, and what does that come up for gallons per minute?
626.
Okay, 626 gallons per minute is what I have to flush. So I take 2,740 divided by 626, and that tells me the minutes.
4 minutes, 4.4 minutes.
1.04?
4. Yeah, 4.4.
4.4 minutes. Now, this little device right here is a fire hydrant meter. It's a flow device. And when I put it in the airplane, it ruined it. It busted the seals in it. They put it down in that thing. And so this thing is leaking now. And I'll have to fix it when I get home. But this is a fire hydrant meter, and I'll pass it around. You'll notice it's got GPM. And this is made for a 2.5-inch hose connection. So I flush my hydrant a little bit, and I put this on here, and I open it up until I get to 626 gallons per minute. And then I got my little stopwatch, and I time it for 4.4 minutes, 4.5 minutes. And then I know that I have what? Clean that line. So I'll pass this around, and excuse the oil on it. It's only vegetable oil, food grade oil. You can't use anything. But I'm going to have to drain it. And here, let me put that on there. Keep it from getting it all over there. Yes, sir. And that's how you do it. Now, you do that for all your different pipes. You do it for 2, 4, 6, 8, 10, 12. And you can create a no more math chart. And then you don't have to refigure. All you do is divide your length by 100 feet, and it gives you the multiplier factor. Does that make sense? All right. Flush carefully to prevent damage. Open the hydrant slowly and close it slowly. You don't want to create a water hammer and actually cause damage in your system, okay? Maintenance and distribution, scale, tuberculation, those pipes back there are excellent. The way that we can prevent that is by corrosion control, stabilization of the water. If you're having trouble with certain things, you can use lime softening, ion exchange, caustic soda, soda ash, all these various chemicals to help prevent those types of problems in your system, okay? And then oxidized iron, calcium carbonate, and removal methods, corrosion, different things, dissolving of metal that damages tanks. How many of y'all have done the coupon testing for corrosion control? And Miss Bessie's going to talk about that, where you put the coupons in there and you measure how much buildup or how much how many grams you lose over a period of time. Have y'all done that? When you did it for lead, it was required for lead and copper. For y'all that did lead and copper, anybody involved in the lead and copper thing? Yeah, if you were involved in lead and copper, you did the coupon testing, where you put the little 3-inch by inch and a quarter, something like that.
The city of Newport has really old, a lot of lead lines.
Oh.
So the EPA required them to build these racks at the treatment plant.
Oh, at the racks.
Go out and cut actual samples out of the road, put them in the racks, and then run metering pumps through them for, I don't know how long, but if you go
Wow.
to a main pump station, there was racks and racks of these old lead pipes. Seemed to be running for months.
Yes.
And they had quite a few of them. because it's the whole island. has
Well, that's-
a lot of whole pipe.
Yeah, y'all, you know, this part of the country is some of the oldest in
Well,
all
they
of
were concerned
US.
about, I guess, Washington DC or somebody went to hydroxide or something for pH control. And
Mhm.
all of a sudden their lead readings went completely off the scales because it was dissolving.
Yes.
And then when Newport saw that, they were upgrading their system and they ordered them to test it before theirs went completely off the charts.
Wow.
But they had actual pieces soaked in.
Yeah,
water.
and maybe that's what those were back there. That might be where some of that came from. Man, I don't know.
It was something that
That
was
came
changing
from
and
us.
caused a huge dip.
Right.
It went from hundreds into thousands in DC.
Effects of water quality, again, remember this. If it's scale forming, it's going to reduce the inside diameter of the pipe. It's going to precipitate out on the walls. If it is corrosion and you have steel pipes, we're going to have a lot of metal ions precipitating out on the interior of the pipe, which is going to increase both what? Friction and increase your head. Thusly, we'll have to be aware of all of that. And also causes metal fatigue. And metal fatigue can end up what? In a lot of water breaks and stuff like that. So we go, and then corrosion, factors that cause corrosion. Of course, whatever's in the water can cause corrosion, right? Low pH, dissolved oxygen, and CO2, which are common in well water. This CO2 is real common in well water, okay? Dissolved salts, different metal ions that are in water that can affect, you know, if you look at a periodic table, 80% of the periodic table is metal salts. So there's a lot of them that can affect you. Free chlorine, because free chlorine, remember, chlorine, when you add it to water, makes two acids, hypochlorous, which is the disinfectant, and hydrochloric or muriatic acid. That's what drives the pH down. The hydrochloric acid drives the pH down. So, and low hardness can also affect the corrosiveness of the water. Remember, the higher the calcium carbonate, the more alkali or the more basic it is, okay? So we go from there. All right. Factors that continued, high velocity. The higher the velocity, the more scarifying of the interior of the pipe. High temperatures. Remember, things are more reactive in higher temperatures. The lower the temperature, the lower the reaction, okay? Alkalinity, again, affects the low alkalinity. There's three types of alkalinity. We have what we call calcium carbonate, and that could be calcium hydroxide, calcium bicarbonate, calcium carbonate. It could be magnesium carbonate, bicarbonate, or magnesium hydroxide. Then we have what we also call hardness is sodium carbonate. Sodium carbonate makes the water soft. But then we have what we call permanent, like calcium sulfate, magnesium sulfate. Those are all permanent hardness. You have to boil the water, or you have to use chemicals to get it out. And Miss Bessie will talk about that this afternoon. Okay, reducing bacteria. There is so much debate on different types of reducing bacteria. We have Pseudomonas. We have, these are all what they call, they're autotrophic. Autotrophic bacteria do not need food. They get their energy from the compounds that are in the water. So if I have CO2, if I have nitrates in the water or phosphates in the water, they steal the oxygen from those compounds to get their energy. Okay? So if I have sulfur bacteria in my water, the sulfur is going to go to the sulfate, steal the oxygen from the sulfate ion, and then you have sulfur left over. Sulfur is going to combine with the hydrogen sulfide to make, with the hydrogen to make hydrogen sulfide gas. Or if you have carbonate, and if I have carbonate bacteria, Pseudomonas bacteria, then the Pseudomonas bacteria are going to steal the oxygen, and then the carbon's going to combine with the hydrogen to make methane. And so it is a autotrophic type bacteria. And Miss Bessie will talk like that, little bit about that this afternoon when we get into that and stuff. And pipe with protective lining coatings. We got cement lined back there. A lot of people are using PVC, high density polyethylene, and acrylonitrile. Anybody use the acrylonitrile butadiene? Don't. You're looking for a nightmare. That's some bad stuff. Anodes on storage tanks. You remember they can only be aluminum or zinc. Eliminate different metals in the system. If you can use PVC or high density polyethylene, do so. Treat water with chemicals. All of those things work. Use dielectric unions. If you can separate metals from metals, like brass from steel or copper from your different metals, you'll help protect them and they last longer. And main repairs. Mains are difficult. Mains are falling apart in the United States. The United States infrastructure is quickly deteriorating, as y'all probably already are quite aware of. The oldest town in Texas is Gonzales. Gonzales and Goliad were founded in 1820. The second oldest cities in Texas is Houston, believe it or not, and it was 1821. And so our towns are new compared to some of the towns in the New England area. Some of these towns have been around, what, since time began? Yeah, and so your infrastructure is getting quite old. We are just now starting to experience a little bit what y'all have experienced for years. So some of our infrastructure now is approaching 100 years old. In some parts of Houston and in San Antonio, we still have some wooden mains that were put in 1915, 1920s. And we even have some old Orangeburg pipe. Remember during World War II, the use of Orangeburg? It was called toilet tissue paper rolls, and they put tar on it, and that was a pipe. So that's a big challenge to us. Proper equipment, proper supplies, that's the biggest question. If you got a various size pipes, you got to keep a large inventory, pumps and everything else, disinfectant. When a leak is found, what do? We got to excavate it. Sometimes you have to isolate it. It's recommended that you fix it hot if you can. But again, when you talk about OSHA standards and safety standards, if you're fixing it hot, remember this, you have to dewater it and you cannot stand in the mud. You're going to have to take extra precautions if you're going to fix it hot. How many of y'all ever fixed a main hot? Yeah, you know, has your feet ever been stuck in the water? Mud? Yeah, don't do that. I don't want somebody to get hurt. You know, I kid around a lot, but really, I have seen most injuries occur because our feet are stuck in the mud and we get turned sideways. And some people's backs, like mine, have not turned that since I was born. You know, think about it. Oh, me. Yeah. And deeper and keep pool ditch water out of the trench. You want to divert it. Use your pumps to do that. Repairing mains under pressure if possible. If possible, repair the leak hot. This prevents interrupted service, reduces risk of contamination, reduces air in the main, ensures the repair holds under service. And what is a cross connection? Cross connection, can you remember those? It's a water of an unknown source, a water treated to a lesser degree, or it can actually be delivered. I mean, it could be from how do you say, an illegal, illicit connection from a person. A lot of people, they put devices in their home, overpressurizes the line, and what can happen? Can get into the system. And so we have to be very aware of that. And TCU requirements, again, state requirements requires us to notify the customer that there's certain things they cannot do within their facilities. Industries have to have RPZs, reduced pressure zone vacuum breakers. Some cases we only require that they have a double check valve. It just depends if it's primary or secondary contaminant as to what kind of backflow device they use. The air gap is the best, Remember, it's 1 inch or 2 times the inside diameter, whichever is greater. But that is not always what? Practical or anything else, okay? Backflow prevention devices, you know, we have, like on a well, we have an air relief valve so that when the well's running, the valve closes. And then when the well turns off, the valve opens, allows air to come back in so that we don't cause damage to the casing. Now, on high places, in a tank, in a distribution system, air collects up there. That air can cause tremendous damage to your system. So we have what we call a vacuum air valve relief. What it is, it's a valve. The ball inside weighs more than the pressure exerted against it. So as air fills up in there, the ball weighs more than the water, so it opens up, or more than the air. It opens out, the water forces the air out, and then it'll close again. And so it's constantly opening and closing to relieve the air in the line. A lot of times they put them on pumps, because if you get air inside of the pump, it's going to cavitate. So what you do is you put that relief valve in there, and so the ball being heavier than air will open, vents the air, and then the water being heavier than the ball will close it again. It's constantly opening. It's called a small orifice valve. Vent, like on a well, is a large orifice valve. You got to get lots of air in quick. But you want to vent the air in a high point of a pump or in the distribution system. So you place those in there. They're mandatory. You can cause a lot of damage to your distribution system if you don't have them. So those are things we look at. And have repair manuals readily available. Has spare parts on hand, and that can be quite extensive depending on how old the town, how many different valves you have, and how many different styles of pipe and all that other stuff. Alert personnel and prepare emergency equipment. It used to really make me angry when I'd go into the barn, pick up a pump, go out there and hook it up, and it didn't run. And you go back and nobody wrote down who used it last. How many does that happen to? Has that happened? Is that common even up here? Golly. I thought Texas was unique. I thought we were the only dummies out there. But you know, how does it go? You go and get it, you go out there and the pump is all froze up, pipe's got holes in it, and everything else is just don't work. And you have to fix it before you can fix the leak and all that other stuff. So make sure everything's working. Make sure every evening that you fill up all your tanks on your backhoes, your equipment and pumps, and make sure they're working, make sure the hoses are good and stuff like this. Fill storage tanks, isolate elevated storage. In the event that a hurricane's coming in, y'all just recently had a hurricane down there in New Jersey, in New York. David Letterman had to shut down. And so how do you say the best thing? Remember, elevated storage tanks, the center of gravity on elevated storage tanks is 100 feet below ground when it's designed correctly. But when it's empty, it's about 100 feet above the ground. So if it's empty, what's going to happen? High winds are going to blow it over. But when the tank is completely full, the center of gravity on that tank is 100 feet below the ground. So that ground is sucking that tank down, holding it there. But when it's empty, it's very vulnerable. Okay, so we look at it. All right. Restock clamps and calcium hypochlorite. Some government agencies require that you keep a mandatory HDH supply. Texas does. We have to keep a minimum of the average breaks that we have plus another 100%. It's required in Texas, so that's pretty good. Review emergency procedures. Everybody should be aware of their responsibility and understand what they're supposed to do. Management needs to know the whole program, but we as operators, I'm an operator, I needed to know what my function was during emergencies. If it was a hurricane or say a tornado came through or maybe a big blizzard. We don't have many blizzards like y'all do, but we do have a lot of flooding. So we have to worry about that. And types of pumps, the most common centrifugal. Centrifugal, remember, as head increases, the amount put out decreases. As head decreases, the amount put out increases. The reason we don't use positive displacement, because it doesn't matter what the pressure is, but it only puts out a constant flow of water. So if demand goes up, it might not put out enough. Plus, if you're using a piston type, you have a chamber, it fills up, and then it pushes it out, and then it opens and fills. So you'll have surging on the line continuously. That's not good. So centrifugal pumps are primarily the pump of choice, okay? Works real good. Should be designed for a specific job, and we have to look at head and quantity and quality of the water too, you know, just a little bit. And the most important part is the cut water right here. That's high velocity. Now, as the water goes through the volute, this is the volute, you notice how it gets wider. The water decreases in velocity, increasing pressure. Now, you'll notice that the outlet is right at the inlet. The water's coming into the eye of the impeller, but the outlet must be right next to the cut water. That is what forces the water back around, okay? And so it works quite well. And the pump is designed for the overall head and the water necessary to supply all of our customers, okay? So as it goes around, the velocity decreases, but increases pressure. Increasing pressure, all right? All right. Suction or lift, we have what we call positive head. If I have a ground storage tank and my pump is down here, the water on the suction side is above the center line of the pump. So I have positive head. But when the water is below, I have what is called negative head or suction lift. Now, a minute ago, do I have anybody with a straw? Remember yesterday we talked about that? He's got a straw and a cup. When he sucks in on that straw, the atmosphere pushes down on the surface of the water, pushes it up the straw and into the eye of the impeller. Now, pushing down on the Earth's surface is 14.7 psi. If you take 2.31 feet per psi, multiply it by 14.7, you come up with approximately 34 foot. So 34 foot of water is equal to 1 atmosphere of air. A perfect vacuum, you could get 34 foot of lift. Impossible. Friction, and when water is dynamic, it starts to vaporize in motion. So basically you can get 23 to 25 foot of lift, okay? And the last couple of things that we'll talk about is deep water. Again, we talked about this yesterday in groundwater. This pump is designed, the bottom pump, say it puts out 1,000 gallons per minute with 100 foot of head. Well, each stage increases head, but it does not increase GPM. So it's 1,000, 1,000, 1,000, but I go 100 foot ahead, 200 foot ahead, 300 foot ahead. It only increases the ability to overcome the height of the column of the water, okay? And using wells, vertical, either oil or water lubricated. If you're using oil, it must be what? Food grade approved. Line must be on before starting and all that. Selection, amount of water to be pumped. The head, we have to look at head. Material to be pumped, the viscosity. Water is fairly viscous based on what? Temperature. The more colder the water, the more viscous. Cost of that pump. Availability, and lastly, the efficiency of the pump. Do not buy a low efficiency pump. The reason is, if it's 80% efficient, then you're going to have more horsepower, larger pumps, to do something that a smaller pump could do with a higher efficiency with a much smaller motor. Okay? You got to take that into consideration. Pumping rates, gallons per minute, or million gallons per day, or millions of gallons per day, it depends. Head, force that the pump works against. Remember, the highest elevation is what we have to overcome. Static, no flow. Dynamic is water moving in motion. And some of the static lift, we talked about that a little bit. Suction head is positive head. Remember, the water on the suction side is above the center line of the pump. And discharge head is from the center line of the pump to the highest maximum elevation. Okay? That's discharge head. And then we have total static head. We go from the top of the water on the supply side to the top of the water at the highest elevation. It could be less than or more than discharge head, depending on your system. Okay? Friction head is caused by the roughness, the C factor of the pipe, the coefficient of roughness, and how many valves, how many joints, how many different apparatuses are in your system depicts friction head. And engineers normally do that for us, and then we take their numbers and plug them in. Total dynamic head is static head plus friction head. Okay? Static head plus friction head. Pump curves. Basically, let's say that I had a pump and it was 180 foot of total head, and let's say that I needed 800 GPM. I'd come up here where this intersected right here. You'll notice that I'm 55% efficient. That's my pump efficiency. You'll notice that my motor horsepower curve right here is at 75, so I'd have to be at least 75 horsepower. My net positive suction head would be right here, so I'd have to have that minimum of suction head. You draw where it intersects, you come over here, I'd have to at least 12 feet of net positive. That means to start that pump, I need at least 12 foot of water above the eye of that impeller. Okay? Now, if I have suction lift, I have to have a vacuum that equals that amount of head. A vacuum lift to start that pump. Now, once the pump is up and running, I can draw it down no longer than the center line of the pump, because you have to lubricate the packing gland or the mechanical seal. If the mechanical seal or the packing gland becomes dry, it overheats and you got trouble. Okay? And so we'll look at it from there. Check periodically. How do you do that? I've got a pump, I got a valve, and I got a head gauge right here. If my pump needs to put out 400 foot of head, I close that stinking valve and I'll look at my head gauge. If it reads 400 foot of head, I know that my pump is what? Still able to do. But if I close that valve and it's only putting out 390 foot of head, that means there's something wearing out on that pump and I have to repair it. Another way you can do it, if you don't like closing valves and listening to all that noise, because it will be scary, is to overflow your elevated storage tanks periodically. And that's good too. Overflow them there periodically, you get all the bird mess off the top of the water. Yeah. And all that stuff. Acting forces on efficiency, remember, that tuberculation in that pipe can cause additional head, right? High suction lift, worn clogged impellers, high discharge head, all of those things. Pump room, remember, this is where the pumps are housed. Motors, if you can keep that pump room cool, the more efficiency that motor will run. Remember, it does not like heat. Keep it clean, good repair, very good valve installation. They'd like you to use rising stem valves. That way you know that the valve is open or closed. But if you do not use rising stem, you need valves with indicator devices on there to show that it's open or closed. Install your check valves. You don't want the water running back from the ground storage back into the well, and you don't want the water in the elevated storage tank to overflow the ground storage tank. So make sure your check valves are working right. Misalignment is the #1 problem between pump and motor. Make sure it's properly aligned within the manufacturer's recommendation. Foreign matter in the impeller, that happens every now and then. Get a board or two in there. Air leak in the suction. Again, remember, air can cause cavitation. Pump rotating backwards, and that means your check valve failed. Cavitation is air coming out of solution. Remember this, on the suction side, you want one valve size larger. One valve size larger, because you keep the volute and the housing full than your discharge. So one size, nominal pipe size larger than your discharge. Water hammer, bad news, y'all know what that is. So pump sanitation, protect pumps from contamination, keep suction lines out of contaminated areas. Vacuum can draw in contaminants, as you know. Maintain positive suction head, and that means your valves and everything and your suction lines are completely sealed. And lastly, electric motors. The most common one is the squirrel cage induction motor. The reason is AC is you can start and stop it with less heat being built up. If you're using a synchronous motor or a DC motor, the starting and stopping is extreme heat and can burn up that system in the heartbeat. A lot of people use synchronous motors. It starts off in AC. Once it's up to full RPM, it switches over to DC. But most common squirrel cage. Follow manufacturer's recommendations for installation, proper maintenance, proper ventilation, preventive measure to ensure long service. Make sure you perform your maintenance on it as scheduled. Insulation for shock protection, and slow closing valves work really well. A lot of times you'll put an altitude valve on it. It'll close when it cuts off, before it cuts off, and it'll open after it's running, making the pump more efficient. And there you can see the insides, the guts of the motor, and the stator, the shaft, and the bearings and all that good stuff, electrical connector, lubrication points, and go to lunch. See you after lunch. Any questions?